Hello, everyone. Good morning, good afternoon, and good evening to everyone who is tuning in. On behalf of SP Egypt Young Professionals, I would like to welcome you all to today's session. My name is Ahmed Haytham. I am a fresh graduate petroleum engineer from Suez University and the e-mentoring head at SP Egypt YP. And I will be your moderator for today. Before we start, I would like to remind you, please drop your questions in the Q&A section below, and please keep the chat box professional and ethical. Now, without further ado, please give a warm welcome to Engineer Ahmed Samir, who will be giving us a short course that consists of 3 webinars on hydraulic fracturing. Engineer Ahmed Samir is a qualified frac engineer with more than 12 years of experience in the oil and gas industry. With extensive experience in all kinds of frac techniques in addition to experience in completion design for oil and gas wells, this includes over 100 frac jobs performed using all frac technologies such as highway, foam frac, foam highway, clear frac, rod shape proppant, and fracturing of extensively deep high temperature formations. He is an author and co-author of many technical papers published at national and international conferences. Also, he is a qualified stimulation training instructor. Engineer Ahmed Samir is holding both bachelor and master degrees in petroleum engineering from Cairo University. His current position is the Petroleum Engineering Department Manager at Agiba Petroleum Company. Engineer Ahmed, thank you so much for coming, and the mic is yours.
Okay, good evening, everybody. I will start sharing for the slide now. Okay, we will we will cover the following topics during the next 3 sessions. First of all, hydrocarbon production rate and increase the reservoir economical life by increasing decreasing the abandonment pressure that we can keep the reservoirs producing under this pressure, increasing reserve recovery by reducing the abandonment pressure. By the way, we will increase the recoverable reserves from the reservoir. Also, the objective of the stimulation is to reduce or to overcome the near wellbore damage. Stimulation of the reservoir management can be used for economically efficient drainage of the reservoir, economically efficient drainage of laminated formation. The delineation of the laminated formation is by, if we have a different we have low reservoir pressure and high reservoir pressure zone, we can reduce the drawdown against the low reservoir zone and allow it to production with high reservoir pressure zone, delaying the honest water production by reducing the drawdown, and sand control also by reducing the drawdown across the perforation. This will control the sand production. This is our main equation for stimulation and for the production. This is the productivity index equation. This is the productivity index equation, and we can see here the term of skin. This is the term that we are playing with, trying to reducing this term in order to increase the Q, which is the production rate, assuming same drainage radius and same well radius. If we are reducing this term, we will, by the way, we will increase the Q production, or the total production from the well. Total skin include the two terms: formation damage skin and pseudo skin. Formation damage skin is related to any operation that happened after drilling the well and reduce the deliverability of the well, include damage formation or stimulated formation. This stimulated formation will be, the skin value will be with negative value. In case the damage formation skin will be with positive value. If we don't have neither damage or stimulation, the skin value would be 0. For pseudoskin, the pseudoskin is related to physical properties and mechanical factor for the well itself. The physical properties is related to the rock, and the mechanical factor is related to the well and the completion skin itself. This is the effect of skin. This is the effect of skin. We can see here the effect of skin on the drawdown. This is this point is the drawdown pressure with positive skin value. In case the skin is equal 0, the point will be here. I don't know that the arrow of the presentation slides appear, yes?
It's clear, yeah.
Yes, okay. So the pressure without skin, if we assuming 0 skin, will be at this point. The stimulation after fracturing, we have negative skin. This means that the point of interception between the line of the reservoir and the pressure will be above the original, or assuming 0 skin value, which is the original rock deliverability without any damage. This explains how that the fracturing or stimulation can reduce the drawdown and improve the well deliverability to the well bore. For the well stimulation, that we have two main types for stimulation. The first group is related to well bore clean out and maximum matrix treatment. The second group is creating new path for the fluid and improve the original permeability of the well. Which means if we have well bore clean out treatment, this means that we are going to clean just the well bore against the perforation, and our maximum limitation here in this case is to reach the skin value equal 0, which means that we return the formation to its original skin value and its original deliverability. However, for matrix stimulation means what means we are treating the pore spaces of the rock, trying to dissolving the cementing material between grains itself to increase the pore spaces. And with this action, we will increase also the permeability, and this will affect on the total skin value and will make skin value equal negative. Because we are creating a new passes inside the reservoir to flow to allow the well bore to reservoir fluid to pass through these passes. Same idea is with hydraulic fracturing. With hydraulic fracturing, you are creating a new channel inside the reservoir to allow all the reservoir pore spaces to produce in highway channel, as we can say, to make a highway contact between the well bore and the pore spaces inside the reservoir. The design cycle for any stimulation job is, first of all, we need to define the methodology and justify and explain our problem, why we are going to do this stimulation. Either that we have normally tight reservoir, or we have damage that we have to need to overcome. So we need to review the well performance and to select the candidate and characterize this candidate. Either we need to do this stimulation to improve the original deliverability of this formation, or to overcome damage that occurred before, after the completion, and return the formation deliverability to its original status. So once we decide our objective from this stimulation, we can then decide the fluid and the additives that we are going to use. And after that, we can design the pumping schedule. We will design the pumping schedule according to required frac geometry. And in the section that we are going to discuss the fracture design, we will discuss how we are going to select the fracture geometry itself. After designing the pump schedule, we will discuss the execution of the job, and then evaluation after this, by evaluation the data frac and the post-job evaluation. So we will start now with the first part of our course is the rock mechanic properties. We will discuss in this topic the Young's modulus, Poisson ratio, fracture toughness, and in-situ stress. First of all, the rock mechanics consideration required to model the hydraulic fracturing process, because it is affecting all the important parameters and the fracture shape itself inside the rock. So the frac itself is its geometry depend on what depend. It is a relation between the rock and the fluid you pump it to create this frac. So you should model your reservoir, your rock properties, and also model the fluid that you are using. And the fracture is the combination or the combined results between the fracture, the rock properties and the fluid properties. Both of them controlling your geometry and how this frac is going to propagate inside the reservoir. So from the rock mechanics point of view, we have elastic material properties, and fracture elastic material properties is properties related to Young's modulus and Poisson ratio, the fracture toughness, and the in-situ stress. First of all, the Young's modulus. Young's modulus is the famous Young's modulus for all the material. If you have Young's modulus for the iron, for copper, for aluminium, also for your rock, you have also Young's modulus. Young's modulus is calculated from this chart. This called, the green area is called the elastic region. At the yield point, once you remove the forces that you applied on any material, we can say is not specified for the rock, we can say for any material, the yield point means that once you release the tension that you applied on this material, it will return it back to its original shape. Above this value of stress in this non-yield point, this means once you release the tension from your sample that you are going to test, it will not return it back to its original dimensions. This is the non-elastic region. The Young's modulus is the relation between the stress and strain once it applied as a tension. What we are calling stress. Stress is the force that you applied to apply the tension on the sample test, the samples that you are going to test. The strain is the deformation that happened after you apply this force. The difference between Young's modulus and Poisson ratio, the Young's modulus is the forces applied as a tension. For Poisson ratio, here Poisson ratio, the force is applied as a compression force. This means that for Young's modulus, you will see the deformation like in the reduction in the diameter of the sample that you are going to test. But for the Poisson ratio, you will see increase in the diameter of the sample after applying the force as a compression. So the Poisson ratio is equal what? Equal the strain affecting on in the direction of the D2 capital and D1 capital, and we can see this D1 and D2 is in the vertical axis, and for horizontal axis is D1 and D2 small. If you divided this both strain effect, we can see that this ratio is the Poisson ratio itself. This table showing some Young's modulus and Poisson ratio value for each type of rock. Limestone is ranging from 5 to 13 10 over 6 psi. The Poisson ratio is 0.3 to 0.35. Unconsolidated sand is 0.2 to 1.3. And the Poisson ratio is 0.25 to 1.35. Consolidated sand is 1 to 8 Young's modulus. And the Poisson ratio is 0.15 to 0.3. Siltstone from 4 to 8. The Poisson ratio 0.2 to 0.3. Shale from 1 to 5. And Poisson ratio from 0.2 to 0.45. Cool 0.1 to 1, and the Poisson ratio from 0.35 to 0.45. If we see this table, we can discover that the Young's modulus and the Poisson ratio measuring how far the formation is soft, and we can see here the shale as an example is 0.25. If we compare it with sandstone, we will see that consolidated sand have a Poisson ratio less than this value. If we compare the shale with consolidated sand, we can see that the Young's modulus for consolidated sand is higher than the shale range. Okay. For formation fracture toughness is what is the concept of fracture toughness? Fracture toughness is the measurement of the resistance that the formation will show to overcome the fracturing effect. So the fracture toughness is the resistance of the formation to be fract. It is important. This term is very important for the fracture design because it is measuring the pressure that you need to apply to keep the fracture is propagated. So this term will affect. We can measure this term from the net pressure, and this will be discussed later. During the fracture design phase, this term will be explained or conducted inside the net pressure value. And we can see from this term here, the R is the distance between the. If we assume this area is the perforation, the starting of the fracture at the perforation phase, and this is where the fracture is propagated at the end of the frac. This distance is equal R. So in case to estimate the fracture toughness, we can multiply the stress intensity factor, which is K here, by 2 by R. This is the distance from the tip of the frac till the formation phase, or the perforation phase at the well bore. This is the distance. So this distance is changing with the time. So because while you are initiating the frac, this R term is keep growing while the frac is growing. So your fracture toughness stress value will keep increasing while the fracture length is increasing. The frac will stop to be growing when you reach value for formation toughness equal to the net pressure that you apply. So you cannot exceed this fracture half length once you reach the maximum net pressure that you can apply inside this fracturing. After this value, you cannot keep the fracture keep growing unless you applied more pressure by applying more pressure at the wellhead. In-situ stress is the single most important factor controlling the hydraulic fracturing itself. In fact, the following: the formation in-situ stress is the total stress that applied on single point or single sample from the reservoir rock. So it's controlling what it is controlling orientation of the frac, height of the frac, treatment pressure, and the proppant crashing and the embedment, and the width and the profile of the frac itself. So we have in-situ stress. We have the effective forces acting on the rock while the rock is in situ. 3 unequal principal in situ compressive stress mutually perpendicular to the rock sample. We can explain this term here. We have this rock cube, as we can say. We have 3 different components for stress applied from all the direction of the frac. We have the overburden from the top, and we have the minimum stress and the maximum stress from two different directions opposite to each other. So we have all of these terms all of these stresses is controlling the stresses stored by this cube. So we can say this in-situ stress is all the stresses stored inside this cube of rock. To create the fracturing, you need to liberate these stresses and overcome these stresses to crack this block of rock, and you need to liberate this force by applying higher pressure, higher forces than its minimum component. So the frac will propagate in direction perpendicular to the minimum stress direction. So we can, for calculating the overburden stress, we can assume the overburden stress is equal 1 or 1.1 psi per foot for each feet from the depths. So if we have the 1,000 feet well, or we are going to frac at 1,000 feet, we will multiply 1 by 1,000 feet or 1.1. So this means that the overburden stress is equal 1,000 or 1,100 psi as a pressure. As we said, for horizontal stresses, we have 2 components. One is minimum horizontal stress and one is maximum horizontal stress. We can assume the normal gradient for the minimum horizontal stress is 0.3 to 0.9 psi per feet. The maximum horizontal stress is 1 to 1.5 psi per feet. We have another term now, is the effective rock stress. Effective rock stress, we have the in-situ stress is divided into, is held inside the rock by two material that we can say. The first one is the rock grain itself. The second one is the fluid inside the rock grain. So when you are trying to calculate the formation stress, you need to calculate the formation stress that carried by the rock. To calculate the effective stress, we should remove the stress that carried by the fluid. So to calculate the effective stress, how we are going to calculate? We are going to calculate the total stress applied on the rock and carried by both fluid and rock grains. Then deduct the value of the stress carried by the fluid by multiplying the reservoir pressure or fluid pore pressure by the pore elastic constant. Pore elastic constant, this equal 0.7 for elastic reservoir rock and equal 1 for the rock like salt and salt domes. Salt dome is working like a viscous fluid. Is not we can say the salt is work as viscous fluid, is not holding the fluid inside the. There is no fluid inside the salt dome itself, and the salt is carrying all the force. Because of this, the drillers that understanding this concept, because of during the designing the well, when they penetrate the salt dome, as an example, they should take in consideration that the casing after finish the drilling and also for mud pressure will hold all the stress of the overburden stress. So they cannot account on the rock grains to hold some of the stresses applied from the overburden. With this same concept, we can calculate the effective stress for the minimum and the maximum by applying the by calculating the stress, the minimum horizontal stress and the maximum horizontal stress instead of the total stress value here, and also deduct the value of the stress that held by the formation fluid. What is the definition of the closure pressure? This is first the first term that we apply here, or from the famous frac definition. The closure pressure. The closure pressure is the global stress average of the formation characteristics determined by relatively large fracture and the net pressure at such in the relatively large. What is this? What is the closure pressure concept? The closure pressure concept, if we have a fracture and this fracture is opened, and this fracture is opened by what? By applying pressure inside this fracture. Okay, the closure is the stresses on the fracture face that trying to close the fracture again. So to keep the fracture open, you need to apply from inside the frac pressure or stress higher than this closure pressure, because of the if the pressure inside the fracture is less than this closure pressure value, your frac will start to close. Okay, how we can measure the in-situ stress of the formation? We can measure the in-situ stress of the formation by using wireline log, especially the sonic log. But this sonic log should be dipole to measure the compression and normal wave and the compressional wave also. Or we can measure it from core test or from step rate test and calibration and injection decline test. Step rate test and the calibration in test are both included in the data frac section, and we are going to discuss in the upcoming section. Okay, another type of stress is the lithology-based stress. Lithology stress is component of two main stress: lithostatic stress and tectonic stress. Lithostatic stress is dependent on the rock Poisson ratio and the reservoir pore pressure, and its value is increasing with increasing the pore pressure and Poisson ratio. Tectonic stress can be a significant component depending on geological activity, especially in the areas that we are facing, like the the Gulf of Suez as an example. We have a lot of fault and a lot of tectonic action, so the tectonic stress there should be calculated carefully because it is affecting on total stress of the rock. So this tectonic stress should be calculated carefully in the area of high tectonic activity. It could increase or decrease the stress. How it could increase the stress? Increasing the stress if we have tectonic stress that use bending or folding for the formation, and this formation is holding this stress. Once you start to frag this formation, you will liberate this stored stress inside the rock. So this means that you have rock is stressed by the tectonic movement and holding this stress, and this means that this area is holding stress higher than the normal around the surrounding field. As an example, if you have a fault and you are going to frag near this fault, if you have folding behind this fault during the movement of the fault, the formation is folded. This means what? This means if you are going to frag in this area, you are going to frag in stress is higher than the normal stresses in other wells in the field. So with the same concept, how tectonic stress could decrease the stress. If you have uplift and you are going to frag in the uplift of the fault, this means what? This means that the uplift rised up or formation with higher stress. This means that this formation is stressed down there and then is moved up. After it moved up, it have a higher stress than normal. Also, this could affect on the frag design. How we can calculate the lithostatic stress? We have this equation. The equation is calculating the lithostatic stress from the term of Poisson ratio here. And this is the overburden stress, and this is the pore elastic constant, and this is the pore pressure. So we can calculate the lithostatic stress from these values. If we have the Poisson ratio and overburden stress, we can calculate the lithostatic stress. Also, the tectonic stress, we can calculate the tectonic stress we have is minimum and maximum tectonic stress. We can calculate it from the Young's modulus and the Poisson ratio and the one second. This is the Young's modulus and this is the Poisson ratio, and this is strain in the minimum, in the direction of the minimum horizontal stress, and this is the strain in the direction of the maximum horizontal stress. This example can show us how come that if we have different rock type, as we have here shale and we have here sandstone. This shale and this sandstone is directly above each other. This means what? They are exposed to the same overburden stress. However, that we have in situ stress for the shale different than the sandstone. This is come from where? Come from the difference in Poisson ratio and the Young's modulus for each type of the rock. So if we are going to calculate the overburden stress for both type of rock, if we have 5,000, this rock is at 5,000 feet. First of all, we are going to calculate the pore pressure. It is 0.4 psi per feet multiplied by 5,000 feet. This is equal to 1,000 psi. Then we are going to calculate the overburden stress, 1.05 multiplied by 5,000. This is equal 5,250. We are going to use pore elastic constant equal of 1. Then we can calculate the lithostatic stress for the shale and for the sandstone by using the Young's modulus and Poisson ratio values. If we are calculating these values, we will see that the shale have lithostatic stress higher than the sandstone because of the difference in Poisson ratio and the Young's modulus for the shale and for the sandstone. if we are going to calculate the tectonic stress, we can see that shale is holding less tectonic stress than the sandstone because of also changing or the difference in Young's modulus and Poisson ratio values. So in this case, if we get the summation for the values of both lithostatic stress and tectonic stress both, we can get that the shale is more stressed than the sandstone. Because of that, once you see a shale barrier, massive shale laminated above or below that sandstone that you are going to frac, you can say that this is barrier and the frac is not going to propagate inside this formation because shale normally is stressed than the sandstone. This slide is showing that the effect of stress on the fracture shape. If we are going to see here, this is the fracture shape for low stress formation. For the low stress formation, the frac is short and have higher fracture height than fracture in high stress formation. High stress formation have, if we are going to frac in high stress formation, these two difference, this shape, if we are going to use this shape, is depend on the fracture models that we are using. If we are using BKN or KGD, we are going to assume the frac shape is like the rectangular like this, or we are using B3D model, the frac shape will be assumed like this. We can compare here between the low stress formation with blue and high stress formation with the black line. High stress formation will be less height. Here you can compare the height. So the black fracture with high stress formation have a less height and more fracture length. The low stress formation characterized by higher height than the high stress formation and less half length. This assuming same fracture fluid pumped for both of the type of rock. This means that if you are going to do a frac and you are going to pump 200 barrel of frac fluids, this means what? This means if you are going to pump this fluid inside high stress formation, that you are going to create frac length bigger than the frac created in low stress formation if you pump it same frac fluid volume. This is comparison for both type of formation. Then we will discuss some fracture fluid and water-based frac fluid. We have 3 different categories for the fracture fluid classified according to frac use of the gelling agent. We can classify the fracture fluid according to classification of the frac fluid used. First of all, we have the CMG. CMG, this means we can say first we have the guar, the pure guar without any additives here in the top. We have here, this is the guar without any derivative. What means a derivative? We have the fracture fluid is the fracture fluid is formed from polymer. Polymer have a chains. If this chain have derivative, this means that we have one derivative. If have 2 derivative, this means that we have a fracture polymer that consists of 2 derivatives. If we don't have any derivatives, this means that we are using the pure guar. So for the CMG means what? Means carboxyl methyl group. Carboxyl methyl group, this include carboxyl methyl guar single derivative. Propyl oxide, this can be termed in HBG, hydroxypropyl guar. This have a single derivative of hydroxypropyl derivative. The type of derivative in the CMG is carboxymethyl derivative. The type of the derivative in HBG is hydroxypropyl guar derivative. This means that we have these two categories. Both of them are having one derivative, but with different type. If we have both of this derivative, we have double derivative process. This is called CMHBG. This CMHBG have one derivative from carboxymethyl guar and have another derivative from hydroxypropyl guar. So this means that we have two derivatives. This CMHBG is the highest temperature rated fracture fluid in the market. So this means what? As much as we increase number of derivatives, the stabilization against temperature for the polymer is increased. So this, the previous slide showing the classification of the water-based fracture fluid according to the gelling agent. Then we can classify the fracture fluid according to the crosslinking system. We have two types of crosslinkers. The first one is the Borate Crosslinker, and the second one is Organometallic Crosslinker. The Borate Crosslinker can hold the temperature up to 350 Fahrenheit, and the organometallic crosslinkers can hold the temperature up to 400 Fahrenheit. However, the Borate crosslinking system is shear insensitive, which means that if the fracture fluid is subject to shear force, like when it is passing through restriction in the frac string or passing through the perforation itself, this means that the shear force applied on the frac itself, frac fluid, increased. This shear force, once it applied, it reduced its viscosity. So after passing this high shear area, that we can say, the fracture fluid can heal itself in case of using Borate Crosslinker. This means that the viscosity is returned back to its original value after passing this high shear rate area. But for the organometallic crosslinker is sensitive to shear, which means that once it loses viscosity due to increasing in shear force, it is not returning back again to its original value. So this is the limitation for organometallic crosslinker. Borate crosslinker, we can add the boron item from using either boric acid or borate salts. Its advantage is it's fast crosslinking for standard system. We can delay the crosslinking time in order to reduce the wellhead pressure if we are going to bump through high lengths or the fracture of deep wells. Can be crosslinking up to 350 Fahrenheit with cooling down. Cooling down meaning pumping of water in the front of the fracture fluid, or the pumping water to cool down the reservoir rock before starting pumping of the bed, so we can reach this 350 with using the cool down water. We can control the viscosity. Crosslinking gel is stable against shear and have a thermal stability. The Borate Crosslinker is reversible, so it means that we can break the Borate Crosslinking system. Organometallic Crosslinking, we are using titanium and zirconium complex to instead of the boron, as we said, to crosslink the guar. It is have thermal stability higher than the boron system. It is developed for hot wells up to 300 and can increase up to 400 Fahrenheit if we do a cool down. Can crosslink in different pH value. It have a less sensitivity to pH value than the borate system, but its problem, it is sensitive to shear. The metal crosslinking is used usually with derivative guar system like the CMHBG, especially because it is applied for high temperature cases. Have a wide range for pH range to create the crosslinking. It's not sensitive to the pH value like the borate system. The crosslinking is reversible, so it is sensitive to shear. Okay, we can stop this day at this point. Any questions?
Thank you, Engineer Ahmed, for this very informative webinar. I'm sure the audience benefit greatly from it. In the meantime, I've collected a few questions for the quick Q&A session. So starting by the first question, Mohammed asking, how is the Poisson ratio effect on the hydraulic fracturing?
As we explained in this slide, Poisson ratio is affecting on the rock stress still. As we said, the rock stress, if we have this example that we explained here, that Poisson ratio and Young's modulus, both of them, we have two different type of rocks like shale and sandstone. Each one of them have Poisson ratio and Young's modulus with different values than each other. However, that both of them are holding same overburden stress. However, that if we calculate the total stress of the rock for the shale and sandstone will be different according to what? According to the Young's modulus and Poisson ratio itself, according to the lithostatic equation and the lithostatic stress and the tectonic stress, as we explained in this slide. Here, this equation for lithostatic stress, if you apply this equation for the, you will see here that the difference, the main difference between the two type of rocks layered above each other is the Poisson ratio value, because the overburden stress is same, the bore elastic, the bore pressure for both zone are same. What is the difference? The difference is Poisson ratio. So the Poisson ratio is affecting on the stress of the rock, which in the same times affecting on the geometry and the fracture propagation. As we said that for the high stress and low stress formation have a different type, have a different frac geometry, have a different frac shape itself. Because of what? Because of if you have high stress formation, that this means that you need the closure pressure of this formation is higher. The closure pressure is higher. This means what? you need higher net pressure to keep this fractures open. Also, the formation toughness, this term that we are discussing previously here, will be different. According to what? According to the formation stress. This will control the propagation, and in this way will control the fracture half length. So if you have less half length, this means that you have higher height. So the Poisson ratio is affecting the formation stress and at the same time affecting the fracture geometry. So once it affects on the fracture geometry, it affects on the frac design itself. Okay.
Okay, thank you, Engineer Ahmed. Okay, we have a second question. Do we have sort of transition area between shale and sandstone, or the Poisson ratio value just have changing that drastically?
We don't have a transition zone. It is just changed according to the reservoir, according to rock type. So the shale have a different Young's modulus and Poisson ratio rather than the sandstone. We can have a transition zone if we have shaly sand or silty sand. This means we have a different type of rock, have a value for Poisson ratio and the Young's modulus between the shale and sand. But if we don't have shaly sand, this means that we will have two different value direct without any transition zone.
Okay, we have another question. How we can change mud weight to avoid to fracture the formation, such as shale, and do not gain a reflux?
This is a well-controlled issue, but this is related to the formation, the formation stress. It is totally different rather than the fracture concept. The fracture concept, we are intent to frac the formation. However, so we are designing our fluid to break the formation. However, for the drilling fluid, that they are designing the mud weight not to break the formation. So they are depend on that. They are depend on the calculate. They get from us the fracture pressure of the formation. So they are selecting the maximum weight for this fracture fluid to have a hydrostatic pressure less than the value of the fracture pressure of the formation. So he will not frac the formation. So then he calculate the this hydrostatic pressure is enough to kill the well and prevent any influx from enter the wellbore or not. But in case that he make this calculation and found impossible to design a fluid to not to frac the formation and at the same time control the well and prevent any influx inside the wellbore. So he will redesign the casing setting point to cover this weak zone and drill this zone with less hydrostatic fluid if we have down the well higher, because normal we have as far as we go down the well, the hydrostatic pressure start to increase. So you need higher hydrostatic pressure to control the well. Especially that if you have abnormal reservoir pressure zone. So you need to separate between the abnormal high pressure zone and the weak formation that you're afraid to break. So you need to redesign the casing setting point to set the casing point just below this weak zone and then continue drilling after that.
Thank you, Engineer Ahmed. We have a question from Muhammad. What is the function of the crosslinker?
The function of the crosslinker, once you mixing the polymer with the water, you have something called linear gel. Linear gel have a less viscosity than the crosslinker gel. Crosslinker is crosslinking. You know that we are using polymer as a gelling agent. The polymer is creating the viscosity by creating long chains. These long chains of the molecules are conducted by adding the crosslinker to link all these polymer chains together to create longer chains. So this is the function of the crosslinker.
Okay. Ahmed Kamil is asking, could you illustrate with real data logs how to get raw properties such as Poisson ratio and Young's modulus?
I can show you something, but not today. I can prepare this tomorrow.
Okay. From Madani.
But this will take a long time because we can spend all the. I have some slides I was including in this presentation, but I remove it because it will take some time. So okay. I can share these slides and we can discuss it later.
Okay.
But because it is have a lot of equations that calculating the Poisson ratio and Young's modulus from the sonic log, and how to calculate it from the shear wave and compressional wave speed.
Okay, perfect. From Madani Salah, can you explain please the execution of fracturing operation, like step by step? What data is needed and the variables to be calculated to make a fracturing program?
Okay, this will be discussed later in this course. Tomorrow will be discussed how we are going to conduct the frac job itself and the equipment used for the fraction itself.
Okay.
Last day will be as for how we are designing the frac and selecting the geometry, and how we are evaluating the data frac data.
Okay. Another question from Ammar or request. Could you give more details about the fracture toughness?
The fracture toughness. Here, the fracture toughness, as we explained previously, the fracture toughness is the resistance that the formation is showing to resist the fracturing force. This means what? Once you start to frac the formation, you are getting resistance from the rock to be fracked. This resistance is called the fracture toughness. Okay? So this resistance is depend on the resistance force is increasing while the distance between the fracture tip, because the resistance is existing here in this zone. Yes? Because all of this distance already fracked, so there is no resistance applied here in this area. All the resistance is applied where? Here in this area. Correct? This means what? As this length is increased, the stress measured here is increased. Correct? This appears from this equation. So we have here the stress intensity factor K multiplied by 2 by R, and this R is the distance between the fracture face at the perforation and the fracture tip at the end. This what is controlling the propagation of the frac. When you apply constant pressure here, this pressure is remaining constant. However, that while the frac is propagated, the fracture toughness keep increasing. Will keep increase until the total fracture toughness applied inside the fracture equal to the pressure that you applied here in the perforation, at the perforation. So once this pressure and this fracture toughness stress is equal, the fracture will stop to propagate.
Thank you, Engineer Ahmed. We have more two questions, if it's possible.
Yes.
Okay, so from Mahmoud Abdurrahman, he's asking, could you give the relation between toughness, Poisson ratio, and the principal stress with the length of the fracture?
As we explain here that the fracture length is depend on the fracture toughness. Okay, and we explained just previously in the previous question the relation between the fracture toughness and the fracture length. However, that the Poisson ratio and the Young's modulus is affecting on the term that we explain as closure stress. Okay, the closure stress is the stress that applied in the fracture from here, from the both side of the frac, trying to close the frac. Correct? So, if you have this stress, this closure term controlling the fracture width, because it is normal. As you have less closure stress, you will have bigger width. Correct? If you have higher closure stress, this means that the frac will be narrow. So this controlling the fracture width. So here, formation toughness is controlling the fracture half length and the closure stress, which include Young's modulus and Poisson ratio, which is included inside the in-situ stress, controlling the width. So what is controlling the height? What controlling the height is the overburden stress and if there is barrier below and above. Okay, the barriers means that formation with different lithology have a higher stress than your zone that the fracture is propagating through.
Okay. Faso is asking, are we going to study more about the proppants in this course?
Yes, after finishing the fracture fluid additives tomorrow, we will discuss the proppants.
Okay. Okay, thank you, Engineer Ahmed, for answering our questions. This concludes our quick Q&A session. So thank you again for dedicating some time of your surely busy schedule and for sharing your experience with us today. Thank you, attendees, for tuning in from all around the world. Please remember to join us tomorrow for our second webinar at 5 p.m. Egyptian time. In the meantime, please stay safe, healthy, and positive. Have a great day.
Thank you. Hoping that I show you some useful data.
Thank you so much, Engineer Ahmed. Thank you.